Hello and good morning or afternoon or evening to you all. With the power outage, I am just going to make this video for you so we can stay on track. So right here, what I have for you is basically where we left off last time. We got through the alkane nomenclature stuff in terms of drawing a hydrocarbon or an alkyl halide. And then this is what we're going to spend our time on today, in addition to lecture 5. So these are a small portion of lecture 4 that we're going to go over, and then most, if not all, of lecture 5. And I'm going to time myself to make sure that I don't do any more than our hour and 35 minutes. All right, so just to scroll through this, we talked about having the parent chain of carbons being the number that we see here in the zigzag associated with the table on the next page. I'll scroll by again. So we have some examples there. We gave some examples and worked on these in class where we added what we call substituents. So these groups here, this one here is our methyl group, for example. This one over here had 2 ethyl groups. We had a chloro group here, propyl group, butyl group, another chloro group. So those are just a few examples that we played with. We did our fun calling out of all the different prefixes. So now we know that 1 carbon goes with meth and 4 carbons go with bute, for example. These are the substituents. Substituent just being, when it is an alkyl group, meaning it's not a full chain, it's just a little branch coming off of the chain. So alkyl group or substituent or a branch is kind of all meaning about the same thing. And then I circled here the 2 weird ones. And by weird, I mean, it's not just a regular methyl, ethyl, or propyl. There's also isomers like isopropyl that you should be responsible for. And an isopropyl group has a carbon with 1 hydrogen attached, but that carbon is also attached to 2 CH3 groups. So it's 3 carbons total, just not in a straight line. Similarly, instead of a butyl group where it's 4 carbons in a row, we have this squiggly line, which means that the parent chain would be over here. So the squiggly line just means that there's something else there. This is attached to something else, and that this is a carbon that's attached to the parent, and that carbon has no hydrogens, but is attached to 3 methyl groups, right? It's each one is attached to another carbon that then has 3 hydrogens. So you are responsible for being able to add an isopropyl and a tert-butyl group to a parent chain. The sec-butyl and the isobutyl, these are less common, and so I'm not holding you responsible for those 2. Okay, we just barely started talking about conformational analysis. And what that is once again the free rotation that we have around a carbon-carbon single bond. And we need to be able to take a 3-dimensional structure and draw it on 2-dimensional paper. We're going to visualize first the structure of ethane, just 2 carbons linked together with 3 hydrogens each. And this is our, it's not a 3-dimensional drawing because it's on 2-dimensional paper, but it's as 3-dimensional as we can get. And then if we take our eyeball and look down that carbon 1 to 2 bond, I'll just number, this is the one in the front, the blue one here is carbon 1, and the one in the back is 2, and we kind of smush it, it's going to look like this. So I'm going to go to my model app and show you a little bit more on that. So here's our model AR app, and it's just ethane. I'm going to drag over 2 carbons. So this is our 2-carbon ethane, and when I rotate, I'll zoom in a little bit first, then when I rotate around this molecule here, right, I'm just moving it around in space, very, very cool stuff, but when I rotate it, I'm going to take this carbon in front, we call that carbon 1, and then the carbon in back, and I'm going to look down the carbon 1-2 bond to the point where that back carbon or carbon 2 disappears. And you can see from here that we have these hydrogens that are all spread out, and the proper term for those spread out hydrogens is that this is a staggered projection. So this is going to be where the molecule spends most of its time because those hydrogens are all spread out. So that's one. Let me just skip back so you can see how we draw that on paper. So this is the staggered conformation, or the staggered, we call a Newman projection. If we were to rotate around that bond, we get to an eclipse conformation. So let's take a look at that. So as we get to learn this program, we see that if we turn this to the side and we highlight, I just tapped on that bond, I can then drag, I'm touching to the left side of that molecule so that this is rotating. And all I did was a 30-degree, actually maybe it was a, whatever, 30-degree rotation. And then I'm going to turn this around again. And not only are the two carbons kind of blocking each other, but you can see these hydrogens are kind of bumping into each other. They're very small hydrogens, but they still are what we call eclipsing each other. So an eclipse would be just, you don't see the one in behind. But with a what we call an eclipsed conformation, when we smush this and we draw this on a piece of paper, we actually do see all 6 of those hydrogens. And this is what that eclipsed conformation looks like on paper. Again, I can't get these exactly eclipsed, especially with my drawing program. If you were to draw them, and you will, when you do get ready to draw them by hand, it's a little bit easier to get those closer. So yeah, we have, actually I should have done the back carbon there in red, that's carbon 2, and then we have the hydrogens that are just right next to each other. So these hydrogens are bumping into each other. And this idea of them bumping into each other, we use with these little squiggle lines, these little lines that cross over. And this is representing those little electron clouds, very small with hydrogen, but when those electrons bump into each other, it's causing what we call steric repulsions or electron cloud repulsions. It's the same idea as like charges, in this case electrons, they're going to repel each other. So the closer together they are, as in a staggered, the closer together they are as in a eclipsed, right? So these are closer together, the more energy that is associated with that molecule. So this is a higher energy to hold it in place. So this is actually less stable. Any eclipse conformation is pretty much always going to be less stable than any staggered conformation. So here, everything is nicely spread out. That's great. That's going to translate to a lower energy, right? It doesn't take as much energy to keep it there. And so this is going to be the more stable one. And this is where we left off for reals. Okay, we're going to give this some more detail, like as we start to make bigger molecules, having more than just hydrogens on there, we're going to need some more lingo to actually talk about this appropriately. So we have a very general term. There's a general term that is steric strain. And steric strain is, once again, that electron cloud repulsion. So if we have 2 electron clouds that are bumping into each other, right, they're going to be repelling, and that's not so great. So that's what we're going to try to avoid. We would say this is unfavorable, that it decreases stability, and it makes it less likely for that conformation to exist, which means it's going to be less stable. And it depends on how big those groups are, right? The bigger the group, the more strain. We're going to have 2 different types of strain. We have, or specifically for Newman projections, if we are looking at a staggered projection, we're going to be on the lookout for gauche interactions. And gauche interactions happen when we have bigger groups next to each other in a staggered projection. In the case of the staggered projection above, we have these little itty bitty hydrogens. They're so small that there are no gauche interactions. So we're mentioning this for anything else. So this one has no gauche interactions, and gauche is just a fancy way of saying that they are not close enough to each other to actually bump into each other, because hydrogen is too small. Torsional strain is the fancier term that we associate with, so torsional strain goes with eclipsed projections. So these pieces that I had over here, these highlighted pieces, these were actually called torsional strain. And this is getting very busy, but we're going to do this for 2 more examples. So torsional strain would be the two hydrogens bumping into each other in each case there. These are definitely not values that you need to memorize down here. Do not memorize these. I don't remember what they are. I don't expect you to. So if you need these values, you'll be given them. Much of the time, you'll be able to look at a couple of projections and just be able to tell intuitively, for example, this is the more stable conformation because it has no steric strain, whereas this one is less stable because it does have steric strain. So there's going to be examples that require a little bit more detail. We're going to start here by looking at the conformation of butane. We're going to first do the zigzag structure or the skeletal structure of butane. We're going to cite down, I have the 1 to 2 bond. I think I actually meant to make that the 2 to 3 bond. So let's do that instead. Let's look down the C2, C3 bond. So here's 1, that's 2, that's 3, and that's 4. If we're looking down the 2-3 bond, there's our little eyeball, right? So we're going to be looking down the 2-3 bond. I find it's very helpful. Students find this very helpful to draw in the other groups that are there. So we have a hydrogen that's going back and a hydrogen that's forward on 2, and the same thing, a hydrogen that's going forward and a hydrogen that's going back here. And don't forget that 3 is connected to 4, which is the CH3 group, and 2 is connected to 1, which is also a CH3 group. I'm going to change this and actually color code it so it looks a little nicer for y'all. Oh, that's better. Okay, so let's take a look down that bond. We have carbon 2 in front that I'll make pink, and 2 is represented by this dot. 2 is going to have a methyl group kind of pointing down. Remember, that's carbon 1. It also has a hydrogen coming out to the top right and to the top left. So that's what's going on carbon number 2. That's how we represent what's going on here. We then have the carbon in the back represented by a big circle. That's going to be carbon 3. I'll just put like 3 right there. And then 3 is going to have a methyl group pointing up, and then the 2 hydrogens coming down here. So let me put that into the model app. So starting with ethane, we can just increase it by 2 carbons. So this is now butane, and just on its own we can like twirl it around and think that's cool, but what we want to do is from this skeletal structure, so this should look like the skeletal structure I just drew, we are going to cite down the 2 to 3 bond, and when we do that, okay, we're just going to kind of hold it like this, and here we see carbon 2 in the front, 3 is hidden in the back. And there we can see that there's 1 methyl group connected to carbon 2 that's pointing down, and then the other methyl group connected to carbon 3 that's pointing up. Carbon 2 also has those 2 hydrogens, and then carbon 3 in the back, I'll just show it a little bit, carbon 3 in the back has those 2 hydrogens, right? But it's shown like this, and it's sort of smushed in that projection. So that's what we had drawn there, and what I'm going to do is I'm going to highlight that bond. I'm going to do a very small rotation to try and get to an eclipsed conformation. So we'll see how I did. I want to try and eclipse 2 bonds. So when I hold it, looks like I did an okay job there. I might do it a little bit more that way. Sure, that's good enough. So what we see is that methyl group is now eclipsing that hydrogen in the back. This hydrogen is eclipsing that methyl group, and then this hydrogen is eclipsing that other hydrogen. So let me try and remember this and draw the best possible structure that is the same as this. So I paused the video to skip over things, restarted, and I can't remember where I left off. So I think this is where I left off. I apologize if I'm repeating anything, but I can't really check until I stop. So we'll see. Anywho's, so we just saw that eclipse conformation, I believe, where we had 2 hydrogens pointing out and 1 methyl group going down. So that first carbon, carbon 2 stayed in place. The one in the back, carbon 3, had that methyl group that moved to the side. This is going to cause some eclipsing interactions or some torsional strain. This hydrogen is going to be eclipsing that methyl group and another one here. So let me move this guy over a little bit. So we're going to be checking for the amount of strain in this eclipse conformation. We'll see that there are two hydrogens eclipsing each other. This is going to be where we look at our table. Torsional strain is going to go along with your eclipsing or eclipsed conformations. So when two hydrogens are bumping into each other, that is going to be 4 kilojoules per mole of energy, and the greater the energy, the less stable, the less favorable. We also have methyl hydrogen, the MEH, right? So we're looking at our torsional strain. This is going to account for 6. So we have 2 of those, another one down here. So these groups are bumping into each other. So this is going to be an opportunity for you all to pause the video yourself and work on the other conformations. So I'm going to pause mine and I'm going to go back to my model program is where we'll come back. Just kidding, we're going to add these up first. So the total energy associated with this conformation is 16. So we just add these guys up. Okay. Whereas over here, there is no strain associated with this one. This is a staggered conformation, and a staggered conformation, we're looking out for gauche interactions. So I'll just write this next to here, that staggered goes with gauche. And what we're looking for are any groups that are right next to each other. And in this projection here, because the hydrogen is so teeny tiny, so very small, even though the hydrogen or the methyl's a little bit bigger, these groups are not bumping into each other. Whereas on the eclipse conformation, we do have these hydrogens, exaggerating, we do have these hydrogens, even though they're small, they're still bumping into each other. Methyl's pretty big, so it's causing greater interactions, and again, we see that here. So these groups are bumping into each other. So this is, again, where I'll pause and see if you can come up with the other eclipsing conformation and the other staggered conformation. So there's 3 of each. We already drew 1 for each. So I like to do a slow reveal with you all so you have the opportunity to check your work before you see the complete answer. So if you were stuck on what to do, you should have at least drawn these like skeleton Newman projections, 2 on the left and 2 on the right. So we can pause again and continue that, or you can continue with me. For each and every one of them, I'm going to hold the front carbon still. So 1 carbon's going to stay still. That means I'm simplifying my problem, and I'm putting the 2 hydrogens and the methyl group all in the same place, and we're just rotating around the back one. Okay. Now in our first one, we had the methyl group pointing up. So in my second one, I'm going to put that methyl group, again, the rotation, I put it right to here. But then if I keep going, I'm over here, my methyl group is down in this quadrant, and my hydrogens are over here. So in this conformation, we actually do have some steric hindrance between the 2 methyl groups. That is going to be our staggered or gauche interaction, and this is going to have an energy of 3.8 kilojoules per mole. We keep going, we find, I'm having them kind of spread out so we can see the different things that happen, but we have, oops, I just realized I did my eclipsed ones wrong. So our eclipsed ones should be eclipsing. Okay, and the other position that methyl group could be, we'll do the staggered ones. The other position the methyl group could be would be down there on the left. This is going to have the same amount of energy as the one on the right. Oh, sorry, this is the one on the left. So they both, I'm just going to move this over here, they both have an energy of 3.8 kilojoules per mole. Over here with the the eclipsed conformations, instead of having that methyl group up and to the right, this is going to be our least stable, where we have the biggest groups next to each other. The reason I know that this is going to be the least stable conformation is because we have the biggest groups that are right next to each other. So I can like highlight these guys are bumping into each other. That is bad for business. We're going to be looking for our methyl-methyl interaction. That's an eclipsing interaction that costs, whoa, 12 kilojoules per mole. That's crazy. And then each of these hydrogens bumping into each other costs us 4. Okay, so the total energy for this conformation is 12 plus 4 plus 4, which is 20. I'm just going to write the number 20 instead of adding the units. And then on our final one, we have hydrogen, hydrogen, or sorry, I'm going too fast. We have that methyl group. We're going to just track that methyl group is now pointing up and to the left. So we have 2 methyl hydrogen interactions, which are each 6. And then that one that is 4. So this is another conformation that's going to add up to 16. Right? So we have our no strain, 0. And this is going to be our most stable, all the way down to this conformation here, this this eclipse conformation. This is our least stable because it has the highest energy associated with it. It doesn't stay like that very much. It's more like this one. And so in our last thing with our model app, we can rotate around there, and I'm going to rotate, keep going. So we're basically like pausing and then looking. We rotate a little bit more, and then we look. We keep rotating. We have another staggered. We keep rotating. I'm going to just keep going until I can see that these 2 methyl groups, boom and boom, those guys are bumping into each other. So that's bad for stability, and it doesn't spend much time here. It more likely spends time with those methyl groups spaced out, very much so in this staggered conformation. So I hope you enjoyed that. Let's move on to another example. And the beauty of this is if you missed any of those details, you can just rewind the video. So I would highly recommend that you pause the video and work on these. So I did another example. All I did was just replace a methyl group with a bromine, really, so you can get some more practice with this. This was going to be one that students were going to do as a group. I'm not going to talk through every single little step. So after you pause your video, and after I pause, it'll restart and it'll just sort of show all of the conformations, and we'll do that kind of slowish reveal. First thing to do is to add in what hasn't changed. So we're going to hold that front carbon with the bromine still, and we're going to rotate the back carbon, the stuff with the methyl and the 2 hydrogens in red. So that's first. Here are all of the completed Newman projections showing rotation around our 2-3 bond, or I guess in this case it's a 1-2 bond. And once again, the idea is here's our eyeball, it's looking down that bond, so we have the bromine there in front and the methyl in back. So go ahead, pause the video if you need to, and check to make sure all of what you have written down is the same as what I have. And we're going to move on and add in, again, pausing the video if you like, and adding in all of your values for gauche and torsional strain. I have these arrows here just to show that in order to draw my projections, I'm tracking where the methyl goes. So it started at the top and then it moved over more to the right. And then we're moving it a little bit down. So that's what these arrows are all about. I'm about to erase those, but I just want to show you that's how I'm keeping track of what's where. So again, pausing the video and adding in all of the gauche and torsional strain values. The first thing I decided to do was to look at all of the staggered conformations and look for any gauche interactions. And this is where the 2 groups are close to each other. So here we have the 2 bigger groups, the methyl and the bromine, right next to each other. We can look down at this table, which again, those values would definitely be given. And we can see that that has a 4.5 kilojoules per mole strain. So we can see that 2 staggered conformations have 4.5 kilojoules per mole of strain associated with them. And then there's going to be this one down below, which has no strain. This is for sure going to be our most stable. right? The more stable one is always going to be staggered. So you can pause, check your work, and start working on the eclipsed conformations and torsional stuff. So that'll be next. Pausing for torsional strain or eclipsing conformations. I don't want to go too far with this without you. So all I did was just highlighted the torsional values that goes along with the eclipsed interactions, and I'm going to go one at a time here. I have a methyl bromine eclipsing interaction. That's a pretty big deal. Those are the biggest groups. So you can imagine, here's that methyl overlapping with, we'll just exaggerate, this big bromine. So there's a big electron cloud repulsion there. And that's why this is so huge. This is going to be 13 kilojoules per mole of energy associated with that. Much, much, much smaller interactions between the hydrogen and the hydrogens bumping into each other. So this is why we'll see just 4 kilojoules per mole associated with that. And we add those up to 21. So that's the overall strain associated with that conformation. So, I mean, at this point, I'm seeing that the biggest groups are bumping into each other. This is probably going to be our least stable conformation because the biggest groups are bumping into each other. But I'm going to put a little question mark there because I do want to check the others. So I think it's the least stable because it has the highest amount of energy. The biggest groups are bumping into each other. So then we talked about how we had our staggered projection. We rotate again to get to our next eclipse. We have these guys bumping into each other for 4. We have a hydrogen and a bromine bumping into each other. We look down at our table and we see that's actually worth 11 kilojoules per mole. A methyl group and a hydrogen are actually not that different in size. So we'll see. And then we have a third eclipse one that is a hydrogen and a methyl. So the hydrogen and a methyl down here is going to be worth 6. So this one, oh boy, this is also going to be 21 kilojoules per mole. All right, so that's a tie. I'm going to pause and just check my math. Okay, good. I'd hate to make that kind of mistake. So these both have the same amount of energy associated with them in the eclipsed conformations. So then we go on. We had our most stable conformation where it spends the most time because we had those really big groups, or the biggest groups in the molecule, farthest apart. We could also have called this the anti-conformation. So then we get back to here. We have a big bromine, little hydrogen. We have slightly bigger methyl bumping into that hydrogen, little dude. We have our steric strain that we note with our little crisscross. The hydrogen to methyl is worth 6 from that table. Hydrogen to hydrogen is worth 4. And then hydrogen to hydrogen, check it, or hydrogen to bromine, once again worth 11. So it turns out that any of our eclipse conformations are all going to be equally unstable. So we can take out this sign here that says this is the least stable conformation. This is me erasing that. We would say that all the eclipse conformations for this particular molecule are equally unstable or unfavored. Okay, so the idea here, once again, we'll go back to our app just to show what is actually happening, because we did a lot of models or a lot of like 2-dimensional smushed pictures. So here's a model of the molecule. The size of the bromine's a bit ridiculous, but it's helpful. It shows us that the bromine's pretty big. One of our first conformations was something like this. This is a staggered conformation looking down the 2-3 bond. We could see that the carbon and the bromine, the methyl and the bromine had Gauss interactions because they're pretty close together. We then moved around there and saw something more like, where are we? Oh, sorry, I rotated around the wrong bond. So here I can rotate around there to show that there's some interaction, eclipsing between the hydrogen and the bromine, for example. You can keep rotating around. It's so funny. And this is more like it's not quite staggered. That's a little more like staggered to see the methyl and the bromine are as far apart as possible. So this is, it's not perfect, but it's just the idea that those guys are far apart. And then all of the conformations, surprisingly, even the one where that methyl and the bromine are eclipsed, that is actually equal energy, because these two hydrogens, right, they're bumping into each other, but it's a very small interaction, just like these guys. These two are close to each other, very small interactions, as opposed to these two. However, it sort of all works itself out when we look at the overall energy. Okay, overall energies of all of them being about the same. At this point, I think it would be great for you to take a minute or three to write down some reflections. I wanted to do this in class, but I'm trying to do my best to make this like an interactive experience, at least with yourself. So go ahead and pause the video, take a minute or two, and just write down a couple of reflections, meaning like, what's a couple of things that you learned from this portion of the lecture? Okay, so I hope you came up with some nice reflections. The very last thing that we're going to do in this section, and this is way zoomed out, but we're going to draw, we're going to sketch a graph for the different energy conformations to give you an idea of, you know, the relative amount of time or the energy that's associated with each. I'm really not too focused on this graph part. It's more about drawing the Newman projections, but I know that there's a lot of this in the homework. Or at least in the reading. So I wanted to get this out there. So before we do the graph part, and again, you may need to pause and draw my sketched graph and my axes with my rotation on the x-axis, the degree of rotation, and then my relative energy. So we start at 0. This is before anything happened. And then our 0, so this is going to be like our 0 degree of rotation. This is where we started. That we had at 4.5 kilojoules per mole. Right, so I'm just going to make this little note, like that little point right there is 4.5. That's 4.5 kilojoules per mole. And then our second one, we rotated, each one is going to be rotated by 60 degrees. So we'll do like 60, 20, 180, 2 something. What's 180 plus 60? I think that's 240. Yeah, sure, why not? And then 300, perfect, and 360. Okay, so when we rotated it the first 60 degrees, we got to 21 kilojoules per mole. That was our eclipsed conformation. That's all the way up here. So when it rotates, it goes from 4.5 to 21. And then the next time it rotates, it went back to another 4.5. And so this is at 4.5 again. And then when it rotated again, it went to back to 21, right? Same. And then when we got to our anti-conformation, it turns out that was 240 degree rotation. This went all the way down to no strain. So that's this conformation right here, the anti-conformation right there. And then our next conformation was eclipsed, was back to 21. And then the 360 degree rotation would just get us back to where we started, to the 4.5. So this is a graphical representation, so you can see that once again, all of the eclipsed are equally unstable. So that's just a graphical representation of what we did above. If you are worried about anything like this, worry not. I'm not so much worried about the degree of rotation, and you may have started somewhere different in a different type of problem, but it's just another way to see that, hey, this is the lowest energy conformation, specifically this one, right? These guys line up. These are the lowest energy. This is where it spends the most time, and then all of these have the same energy, which is equally bad, so it doesn't spend much time there. We are going to move to lecture 5 stuff, and I very much hope that you all come to office hours, whether it's mine or the TAs. You go over stuff in discussion, and I hope this is helpful. So yeah, we're going to take a mini pause and move over to lecture 5. Okay, everybody, so we're going to start talking about cycloalkanes, and that means we get to talk a little bit about marijuana. Marijuana has a couple of, or a lot of different, what we call cannabinoids. These are molecules like THC, CBD, the ones that have their psychoactive effects, and sometimes therapeutic effects, in the case of CBD being a little more of a anti-inflammatory. So this is just an example to like bring back functional groups, a couple different concepts that we've seen. And you may notice that this is cannabigerolic acid. This is the precursor to all of the cannabinoids, whether it's CBD or THC, and it has two alkenes. It has a nice big arene, this stuff in here. It has a carboxylic acid, and these alcohol groups, it's okay for you to call these alcohols. That's fine, because that's what we have in our functional group table. But really, if we're going to be proper, these are actually phenols. That's going to be helpful. Phenol stuff we see anytime we have a six-membered ring, alternating double single bonds, and an OH group. And this is going to be useful for you to know it's a phenol in terms of pKa's. So we're kind of bringing a bunch of different things together. Phenols have pKa's around 10. Carboxylic acids they're more acidic. They have pKa's of 5. So what happens here over several steps, that's what these arrow means. This just means that there are several steps. We actually close the ring, which is pretty cool. We'll learn about that chemistry more in Chem 8B, but we close the ring and some of the functional groups change. This OH group is no longer, the OH group there on the left was an alcohol, and now it's an ether. So that's really what organic chemistry is all about, is conversion of different functional groups. So whereas before we had this alkene and the alcohol, those two combine to make an ether, and then we still have the same functional groups. We have the alkene, alcohol, and carboxylic acid. This then undergoes decarboxylation with heat, right? So whenever you smoke weed, whenever you vape it, if you were to bake with it, then you are providing that heat, which means it's going to undergo decarboxylation. This is a process where we lose a molecule of CO2 from there, and it replaces it with a hydrogen. This is the psychoactive form. This is the one right here that gets you high. It can fit into the receptor that then triggers its psychoactive effects. So it's just the little loss of a carboxylic acid that completely changes the reactivity. So if you were to ingest an oil, like if you made a room temperature extract of this, if you were to take marijuana flowers and soak it in, say, like olive oil or avocado oil over the course of a couple of weeks, it'll extract the THCA, right? So you'll have this in a jar and you'll have the THCA into here, and if you ingest this, you won't feel anything. But if you were to heat it, if you were to decarboxylate, so do a heated extract and put that into your oil, or rather, you heat up the oil along with that THCA, it turns it into THC. And if you were to ingest this oil in some form, as avocado oil or olive oil, then this is the stuff that will cause those psychoactive effects. And be very careful, because these tend to be very, very strong and you can definitely overdo it. So dose carefully. But anyway, that's what functional group stuff was all about. And this is just a little introduction into some cycloalkanes, just tying together carbons into rings. Hope you enjoyed that. Yeah, carbon chain tied together into a ring. So let's do some of the nomenclature type stuff. We have 2 4-carbon molecules. We know that because we see that but, the BUT. We have a 4-carbon chain, just regular old butane. If you tie it together into a ring, you get cyclobutane. So you can pause the video and draw hexane and cyclohexane, or you can just do it with me. Hexane is 1, 2, 3, 4, 5, 6. Cyclohexane, you'll get practice drawing these, maybe even as part of the Instagram challenge to design my hairdo. I've been doing these cyclohexane or these hexagons in my hair for a little while, so I'm looking for something different. But yeah, the big difference here, not only in the ring, but is in the number of hydrogens. This has, or should have, if I'm counting this correctly, 14 hydrogens. And I know that kind of off the bat because it's going to follow this formula, CnH2n plus 2. This is the maximum number of hydrogens you can have per carbon. Okay, and then over here, this one actually only has 12 hydrogens. So you can pause the video and count those out if you don't believe me. Go ahead and start thinking about these next two examples. We'll see that we have two different parents in these two examples. One where there's a parent hexane, and another where the parent is cyclohexane. We see on the beginning of there, this is a substituent or a branch, the 3-cyclopentyl, whereas over here an isopropyl is going to be a branch. So I recommend pausing the video, drawing those structures, and then I'll draw them with you. We'll start with our hexane over here. We number it because that's the cool thing to do. And then we'll add our branch. And our branch is a cyclopentyl group. So this is a common thing that students want to do. We want to make a 5-membered ring coming directly off of that. But that is not what we're going for. There actually should be a bond in between carbon 3 and that chain. So instead, we draw this line, the bond. This is a cyclopentyl group. So in general, a cyclopentyl group would be not just the 5 carbons, but then that squiggly line thing, right? That's a cyclopentyl. So here we see that because the parent chain had 6 carbons and then the ring had 5, that hexane won as the parent. So you're going to count either the straight chain or the ring as the parent, not both. So don't add up and find like an 11 carbon chain. If the ring is bigger, so this ring has 6 carbons and isopropyl has only 3, so the ring is going to be a 6-membered ring, a cyclohexane, and there's no number in front of it because that isopropyl group could be anywhere because there's only one group. The isopropyl, the branch, remember, is the 1 carbon with a CH and 2 CH3s coming off of it. So these are just 2 examples. You'll play with more in the homework, but I hope that's enough to get you going. As always, it's great to pause and rework any of this on your own. What we're going to do with these is play with some what we call stereochemistry. And so I think of stereo in terms of like surround sound. And that's kind of how I get back to remembering that it's all about 3D shapes. So what is the 3-dimensional shape of cycloalkane? And a little more specifically, it's of the groups around the cycloalkane. So what we did with Newman projections is going to be really different because we don't have single bond rotation. We say there's a barrier to rotation. So we cannot rotate around those bonds. There's very, very little rotation allowed without actually breaking the bonds in the ring. That means that we've created a plane. Now, this ring, for example, this cyclopentane ring is not actually flat, but we're going to say, like for purposes here, that we have created a plane, and that the groups that are on that plane could either be on the same side or on opposite sides. And so this is where we introduce our Cysts and Trans designation. So trans goes with opposite. If we have 2 methyl groups, for example, on cyclopentane, and they are trans to each other, then you're going to have one group, I'm going to say that this is up, and then we have another group, and I'm going to say that this is down. I could have just drawn it kind of the opposite, where I put the down over here and the up over here. There's a lot of different ways that you could draw this, but just showing that those 2 groups are on opposite sides, and I do that with my bold wedge, meaning forward, and my dashed line going back. If they're on the same side, then here we have these two groups that are either both pointing up or they're both pointing back. So that's kind of the idea, and these you can't switch one into the other. So these are actually different molecules, right? So these are very different molecules. We would call them stereoisomers, or we would call them simpler cis trans isomers. Okay, these are not the same compound. You can't convert one into the other. So let me, you can go ahead and pause the video and try and come up with the structures of these two, trans 1-isopropyl 4-methylcyclohexane and cis of that same jargon. I'm going to do a slow reveal and just start by drawing the cyclohexanes. You can number the ring in a lot of different ways. I'm going to choose to just go 1, 2, 3. I'm only going to number to 4, just because that's where my substituents are. I have an isopropyl group on 1. I'm going to just arbitrarily choose that it's going to be wedged. I'm going to be pointing up. Because it's trans, my methyl group has to be pointing in the opposite direction. Okay, so there are different ways that you could have drawn this. You could have, or you may have come up with something like this, where instead of this being wedged and dashed, it could be dashed and wedged. And I'm going to pause and just show a couple other ways that you could have drawn that molecule. Okay, so I have here, once again, just a couple different ways that you could have drawn trans 1-isopropyl 4-methylcyclohexane. One thing to keep in mind is that these two, you could flip one to make them look like the other. These are actually the same compound, just drawn differently. Whereas up above, and we'll play more with this later, so if this doesn't jive with you right now, don't worry about it. These two are actually different. Okay, you can't superimpose one on the other, whereas with these two, you can flip one and it does fit on the other. Is that true? Yeah, so the wedge becomes a dash. Let me pause and just double check, because I hate saying wrong things in videos. Yep, that's the case. Okay, so those are the same. The ones up above are different. Then if we draw cis 1-isopropyl 4-methylcyclohexane, I'm not going to draw as many examples. I'm just going to show that these two should be on the same side, the methyl and the isopropyl. So those are just a couple of examples to get you going with the cis trans designation. Cis same, trans opposite. So now we get to the ring itself. Now the idea is all of the carbons in any of these rings are all sp3 hybridized, and sp3 hybridized carbons want to be tetrahedral so they can spread out their electrons as much as possible and get some space. Now here, this bond angle is definitely less than 109.5, and we'll go into the actual angle. This one's 90-degree angle. This is definitely less than 109. This is getting a little bit better. You know, it's closer, and then this one is pretty close. Now, here's the thing, is that these are not actually flat in real life. If we were to look at a cyclopentane or a cyclohexane, they actually have some, a little bit more rotation around these bonds. Specifically, like, you know, any one of these bonds, whereas these two are super limited in rotation. So these are actually pretty close to flat. These have what we call ring strain. They're very unstable. These, anytime you see a 3-membered or a 4-membered ring, these tend to be pretty unstable. They're not super common in nature, whereas the 5 and the 6-membered rings are much more stable because their angles are closer to 109, the bonds and the electrons are spread out. So these are actually pretty commonly found in nature, and you'll see those 6-membered rings once again in our marijuana extracts. And then cholesterol is another nice example. Cholesterol has 6 and 5-membered rings. Now we're primarily going to talk about the conformational analysis, the kind of different structures that cyclohexanes can take on. So the rest of this lecture is going to be all about cyclohexane, and the other ones is just, you know, can you draw them given the name. So when we specifically look, this is kind of crazy. So you might want to pause and just sort of look at these look at these structures one at a time. But we have some different representations of a 6-membered ring. And so down there to the left, you see it's numbered 1, 2, 3, 4, 5, 6. This is what we call a chair conformation. The idea is it looks like a lounge chair. There are really, really nice tutorials, so use them. So please use the tutorials in the Klein text to draw the perfect chair. If you're not able to draw a perfect chair, you won't be able to draw the rest of it, being the substituents or the branches off the ring. So make sure you're using those. I have lots of practice in drawing chairs. It's either what I just did there on the left or what we call a ring flip, the one there on the right. So we're going to play with this idea of a ring flip. And a ring flip is maybe not exactly what you think. It's a little bond rotation. It is not flipping upside down. And this is where I'm very sorry that you can't actually see what I'm doing, but it's not flipping upside down. The idea here is that we are taking, let's just look at one carbon at a time. We're taking this one carbon that has the methyl group on it, and that's this one carbon here. And if we draw those bonds pretty much just like this model, right? So here's the model where we can hopefully see this 6-membered ring. And if I'm highlighting the carbon that has the substituent on it, the methyl group, this group is going to be pointing directly up. We call this an axial substituent. So this is pointing up and along the axis of that carbon. So each carbon is going to have an axial group that is pointing straight up or down. In this case, it's pointing straight up, right? That's represented over here. This is our axial and up one that we draw in our chair conformation. And then we have all these cool bubbles so we can see more in 3-dimensional space-ish what's actually happening. And then on that carbon, we also have this hydrogen, right? This is just a hydrogen, and this is what we call an equatorial substituent. Not really a substituent because it's a hydrogen, but each carbon is going to have an axial and an equatorial. And each carbon is also going to have something that is up and is down. So we can hopefully see that that hydrogen is pointing a little bit more down. It's not directly out to the side. Now, going back to this axial substituent, we're thinking about electron cloud repulsions. And here they're showing that because those groups, specifically those hydrogens, or the part of the methyl group, can bump into the other axial hydrogens, it causes what we call 1,3 diaxial interactions, also known as flagpole interactions. So you're picturing those two flagpoles sticking up, and then they're bumping into each other. So another way that I like showing this is here's this methyl group here. I'm exaggerating, it's really not that big, but then you have the clouds caused by those axial hydrogens that are, I know this is exaggerating, but they're sort of bumping into each other. And that only happens with the other axial hydrogens that are on the same side of the ring. So these axial hydrogens are also pointing up. And you can see that here in the picture there, the chair versus the model. These should be telling you the same thing. Now, if we take a look at what we call this ring flip, the ring flip is not a flip of the ring, as you might think, but instead it's a very small rotation of the bonds. It's a very small rotation of the ring. I'm going to say the bonds in the ring. So one way that we like to see is we think about this carbon 1 starting to point down a little bit more. So you can see how this carbon 1 is now pointed down. Now this methyl group, this is pretty key, this methyl group is still pointing up. So if we were to define the plane of that carbon, we can see that methyl group is still pointing a little bit up, and we can also see that over here. Because it's not directly pointing up or down, we call this now an equatorial substituent, and it is still pointing up. That's the thing that is going to stay the same. In a ring flip, it's still going to be pointing in the same direction, up versus down. It's just going to switch from axial to equatorial. And that hydrogen that I had highlighted on the opposite one, just like it's this same carbon we're looking at, that's carbon 1. Here's our chair. It's our general idea. And then we have our hydrogen that is still pointing down, but this is an this is an axial hydrogen because it's pointing directly down. So it's not drawn over here, but I'll add it. This is pointing down, whereas over here, this is pointing down and it was equatorial. So in these when the group is equatorial, we see no strain, right? So there is strain or steric interference caused by axial substituents. So if you have axial substituents, this is going to be your less or least stable conformation, back to conformational analysis. And when you have axial substituents, this is going to be not more axial, more stable. So we'll see some examples of that. You may want to pause this video and just sort of see what you want to take away from this. And just one takeaway that I didn't say explicitly, no strain is caused by by equatorial substituents because they are too far away from anything else to be bumping into each other. One thing that you may see in the book is that equatorial substituents may cause, you may see some gauche interactions. You can see that if you were to draw a Newman projection of these. I'm going to do this one example. I on purpose don't like have it set up in the notes because this is not something that I'm going to hold you responsible for. But because it comes up in the reading, I just wanted to draw attention to that. So this is just sort of like bonus. You're not responsible for ring Newmans. Let's see what I mean by that. But this is crazy. So we could have two Newman projections next to each other. Haha. And that is actually, if we can do a little bit of counting, there's actually a 6-membered ring in there. So we'll say like this is carbon 1, that could be 2, 3, this carbon in the back would be 4, that one there is 5, and then this other carbon, the big circle in the back, is 6. So again, we're not covering this. I'm not going to hold you responsible for drawing these double Newman projections to show how to make a ring, but you may consider that if, let's see, where's carbon 1 with that methyl group. All right, in this case, there's only hydrogens around here coming off of the ring, so there's no gauche interactions here, but there is some strain associated if there's other examples, right? In other examples, there might be some strain. So there's no gauche interactions here because the hydrogen is too small, right? Little baby. So there's no gauche interactions, but if you read about gauche interactions based on equatorial substituents, that's just not something we're going to cover. Okay, so we're just going to keep it simple. There's a lot of little aside, but we're going to keep that simple. Hopefully we can make this more clear as we go on. Okay, so again, this is now going to re-simplify in a way. We're going to look at, again, the restricted rotation in 6-membered rings. We look at cyclohexane by itself. I just added all the different hydrogens in blue and in red. Any of the ones that are bold and in blue are forward and towards you, and then any of the red ones are going behind you. If we were to turn this on its side and to turn each one of those carbons as close to 109.5 as possible, we end up with this chair conformation. And there's always going to be two. I always think chairs and pairs. There's going to be two ring flips. And remember, this flip is not like all the way upside down. This is just a little baby rotation. And it's going to cause any axials to become equatorial and any equatorials to be axial. The thing that will not change is very important. The thing that will not change is what direction it is pointing. So, and that by that I mean the up and the down. So the axial and the equatorial, they will switch in a ring flip. But the up versus down should never change. Or it stays the same. So if we track any one of these, I mean, they're already highlighted, but I can highlight a little bit more so you know who I'm talking about. If we take a look at this conformation here, this hydrogen is pointing up an axial on carbon 1, and in its ring flip, it's still up, but now it's equatorial. And so this is where models are really awesome to help you play around with the different angles. There's also an app for that. There's an app for everything, and that's the Chairs app. So I'm going to take you to that just as a little mini demo. A couple other things I might say about this first. I think it's actually Chairs with an exclamation point, and that's an app that's free that you can play around with. So the first things first is getting practice. Use your tutorial and draw this actual ring. You might just be tracing at first. From there, I think the best thing to do is to start by drawing the axial substituent. So again, I'm just going to be tracing. You can trace with me. Pick a carbon. Let's start on carbon 1. And if these groups in the ring, they're more, I'm going to do these little arrows. You see how these bonds are more pointing down? Well, that means in order to spread everything out that my axial is going to be up. And if I draw the axial up on one carbon, that means it's going to be down on the next, and it's going to be up on the next and down on the next. So my axials alternate up and down. Okay, my axials alternate up and down. And that's exactly the same on both of them. So if I go back to carbon 1 over here, I see that the bonds in the ring are kind of pointing up. So that means that my axial, in this case hydrogen, is going to be pointing down. So if I go then to carbon 2, the axial is pointing up, 3 is down, 4 is up, 5 is down, and 6 is up. So again, the axial substituents alternate up and down. The equatorials also alternate up and down. On carbon 1, since our axial was up, that means our equatorial is down. And check it out, that angle is super important. I did my best in my drawing program. It's not always easy. But this bond here that I just drew, highlighted a lot of different things. So I'll just do that. So this bond that I just drew is parallel to the best of my ability to 2 bonds away in the ring. We can see that for each and every one of the equatorial substituents. So this is why if you don't have a perfect chair, the rest of your bonds aren't going to be great. So on carbon 2, I should probably fix this angle a little bit. I fixed one down below. So on carbon 2, if I were to really fix this, I'll just like erase and then redraw. We'll do an example below. Carbon 2, the equatorial substituent should be parallel to these 2 bonds, 2 bonds away. So it's going to be kind of pointing out in this direction, and because it's pointing up, I'm going to make it blue. So this is going to take some practice. Again, really use the tutorials in the Klein text, and I've taken you through a bit of it to actually draw proper chairs. Might start by tracing, might start when they look a little bit janky, but one thing that you want to avoid for your chairs, we want to avoid drawing bow ties. And we want to avoid drawing lightning bolts, okay? So these are not going to make for nice chairs. They are going to make for really weird bond angles. So that's the general idea. I hope you're starting to wrap your head around this. Let's take a look at the chairs app. So here we are in chairs. It's kind of nice in the beginning because it actually gives you a little animation of what's happening. So there's one chair and it's kind of shifting its bonds and sort of rotating around. And this is what we actually mean by a ring flip. Okay, so I'm going to play. The best I've done apparently is 15. So I'm going to play. So what it's doing is it's giving me some time to say, okay, here is the chair below. See how the one below is axial. I'm going to pick out, all right, well, if I try and make this group up, it's going to say nope, 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 until I give it the correct angle. If I were to do a ring flip, it's then pointing down. Hooray. So then I look and I'm going to try and draw the ring flip of this structure. I should still have my group down. So I'm just touching that dot. If I try and do it up, it tells me no. So I bring it around until I get to the proper angle parallel to the others. I release, and there's my response. This next one on the bottom is pointing up, right? So if I make it down, that's incorrect, and I'm going to be wanting to point it up. And it went from equatorial to axial, straight up and down. And it gives you a little leeway, but straight up should be best. This one is down. And so if I do the wrong angle, like I do out to this side, not so much, but here it should be parallel to the others in the ring. So that's what you can do. You can play with chairs, and that's just gonna pause it there. And we shall take it to the last bit of this class. I actually think I'm doing okay on time. Thank you all again for your patience with all of this. All right, so now we're going to draw conformations for each, and I wanted to start by giving you a hand and just giving you the skeletons. I numbered it for you already, so here definitely pause the video and do your best to try and add some substituents there. All right, so let's work through this together. I'm starting with the cis compound. The question or the problem here is to draw both chair conformations, and then the ultimate goal is to determine the least and most stable for each. So these are actually separate problems, right? So we're not going to be determining whether cis or trans is more stable. I mean, I generally should say that trans tends to be more stable than cis because they're more spread out, but that's not what this question is asking. We're going to draw 2 ring flips for each, chairs and pairs, and decide which one is better, which one is more stable. So here we see again the cis and trans 1,4 isopropyl methyl, whatever. We have the group on 1. I'm going to note that this is pointing up because it's a wedge, it's coming towards you. And the group on 4 is also pointing up. I guess I didn't need to highlight those, but that's what's up. We then have over here on carbon 1, which I labeled, so we all are making the same relative idea here. I'm going to continue numbering around the ring too, because I want to make sure that we're all on the same page. So we have to number it the same way on both of them. So notice I numbered clockwise. I'm going to number clockwise again. So here, 5 and 6. So that actually is pretty important, that we are keeping them as basically making as little change as possible. Now, our group on carbon 1, we want to be pointing up. We look on carbon 1 and we see that the bonds in the ring are pointing down, and that tells me that in order to spread things out the most, that my axial group must be pointing up. So I'm going to have an axial group pointing up, and maybe it's hydrogen, maybe it's isopropyl, I don't know, we'll see. But that's pointing up, and this is axial. And then we have another thing, always going to be 2, that's going to be pointing down, and this is equatorial. Because we already noted that the group on 1 is up, turns out that on this chair conformation, that isopropyl group is indeed going to be axial on this conformation. The group that's pointing down is just a hydrogen. That's the one that's not explicitly shown here, and you don't have to draw it. This is just me showing all the different possibilities. So you can keep that in your notes if you want. I'm going to erase it for simplicity. So you can erase all that stuff if you want. Our axial group is pointing up. On carbon 4, we take a look over here. The bonds in the ring are pointing up. So that means, to space things out, that my axial group should be pointing down. Okay, so I already have its axial and down. So the other group that's equatorial should be pointing up. So it's equatorial and up. And remember, this equatorial bond, in order to make the perfect one, is going to be parallel to the bonds that are 2 away. And that's going to really represent how those bond angles are as close to 109.5 as possible. Even though this looks flat, it's actually very three-dimensional. Okay, so what we're looking to do is to put that methyl group, we're focusing here, we want to put that methyl group up, and here it is. The methyl group is going to be up in equatorial, and then the hydrogen, not shown here, but I can add it, that's the one that's pointing down. You can choose to keep that or not. So I'm going to erase it. Okay, so that's going to be our first chair conformation. We have some things to keep track of because we have an axial substituent. We're going to have 1,3 diaxial interactions. Now, the 1 and the 3 is a relative relationship. It is not necessarily on numbers 1 and 3. It's just 2 carbons away from the axial substituent. So there's our isopropyl axial substituent. If we look 2 carbons away on carbon 5, that has an axial hydrogen also pointing up. So this is axial and up. And then carbon 3 has an axial and up hydrogen. These guys, even though it looks like they're really far away, the isopropyl group is pretty big. So that isopropyl group, we can just like really exaggerate, it's gonna be crazy, but this is really big, and so it's gonna bump in to those hydrogens. So those are the 1,3 diaxial interactions. There's actually 2 sets, right? So sometimes I think in the previous picture they just sort of drew it like this. They're bumping into each other, and then these other groups are bumping into each other. So whichever way you like with the shading stuff, but those are the 1,3 diaxial interactions. On the other chair conformation, we have still those 2 same groups. We should still have the isopropyl group pointing up. It should still be on carbon 1. If we look at what's happening on carbon 1, these groups are pointing up. So our axial must be down. The thing that has to stay consistent is that the isopropyl group should be up. So I'm not going to be putting my isopropyl group in that axial position. Instead, it's going to go equatorial. Remember, this is parallel to 2 bonds away. This is, just kind of label this is our equatorial substituent, and it is pointing up. And that's the thing that has to stay the same. It has to stay up because of our original structure. Okay, the thing that is pointing down was just that hydrogen that we had drawn on the previous structure that you're welcome to leave out. But the thing that we definitely do need to keep is that this isopropyl group is there. So you can decide whether you want to keep that hydrogen there or not, but that is the position of your isopropyl group. From there, we don't have to add what's going on 2, 3, 5, and 6 because they're all just hydrogens, at least for now. And then on carbon 4, we have still a methyl group that needs to be pointing up. The bonds in the ring are pointing down, so that means our axial group is pointing up. So again, we have up and axial. We do want our methyl group to be pointing up. So in this case, our methyl group, which was, this highlighting is okay, the methyl group was equatorial and up, but now it's axial and up. So it's a very small little shift. Remember, it's not a flip upside down, but this is our second conformation. You can add in that hydrogen if you should choose to do so in the equatorial position, but it's not necessary. So I can simplify a little bit. This is these are the 2 chair conformations for the cis compound. This one also has 1,3 diaxial interactions. You will have them anytime you have an axial substituent, and that is caused by the hydrogens that are pointing up an axial that are 2 carbons away. In this case, it happens to be between 2 and 4, causing 1,3 diaxial interactions, and between 4 and 6. But again, that's the relative relationship. So now we compare. We have 1,3 diaxial interactions caused by a big isopropyl group versus those caused by a methyl group, which is relatively small. Okay, so we're going to see that this has greater or larger 1,3 diaxial interactions. This is going to be so busy. This is going to be the least stable conformation here on the left with a bigger axial substituent, and this is going to be the most stable. So let's see if I can highlight that. This is the least stable, that's the most stable. Highly recommend that you pause there and work through any of this on your own, taking for some reflections before you move on to the explanation for the trans compound. Right, so first thing I'm gonna do for the trans compound is I'm gonna draw my skeleton chairs, and here's a tutorial. So you draw these two parallel offset lines, and then from there, I'm gonna have these temporary little dotted lines. You kind of drag out a little farther, put a little dot here out to the side. We connect those. And I'm gonna erase this stuff. I might keep some of it. And then from the other bottommost point here, I'm gonna drag that out a little bit to the side, put a new dot that's gonna represent the 6th carbon, and then we connect those. Okay, so that's gonna make you a really nice chair before you can be a pro and just sort of draw it freehand. So you're gonna have 2 of those, same thing, 2 parallel offset lines. I have this guy kind of out to the side, connect them, and then this guy out to the side and connect them. So that's a pretty good chair. You know you're drawing a good chair if all of your lines have a parallel. So these guys look pretty parallel, that's cool. These guys are parallel, that's cool. And then these guys are parallel. You should not have any vertical lines, again, looking out for these guys. So you shouldn't have any vertical lines or anything kind of overlapping like that. So that's gonna be 1. Because we have some stuff, we're gonna use some of our work from before, we can see that that methyl group should be in the same position as it was in the examples above. So let's not add more work, let's use what we just did. This methyl group should be pointing up and equatorial on one structure. We did all the numbering exactly the same. And then over here, it should be up and axial. So that should be exactly the same as what we did on that structure. The thing that's changing is the position of the isopropyl group. So we'll highlight that. This isopropyl group is here on carbon 1. And instead of pointing up and axial, that's where the hydrogen is now. And we can erase that later, but for right now, we'll keep it. And then our isopropyl group is going to be down and equatorial. Okay, so again, it's down on that first structure. So it needs to be down over here. And we say this is equatorial. This is along the equator of the ring. And I did my best to make it parallel to those opposite ones. Since this is all equatorial, we would say that there are no 1,3 diaxial interactions associated with this conformation. This is definitely going to be our most stable of the trans conformations. There's no axial, or they're all equatorial substituents. That's going to be in contrast to this next one. Here on carbon 1, we'll add our isopropyl group. It still needs to be down, but now our down is axial. You can draw your hydrogen if you like, just to show that it's up and equatorial. But again, now we have 2, oh my dear, 2 axial substituents. Each of these is going to have 2 sets of 1,3 diaxial interactions. So there's the hydrogens that are pointing down, put in blue, and those are going to bump into the isopropyl group. So there's a strain, bad strain associated with that. And then for the methyl group, we're also going to have 1,3 diaxial interactions. Those are going pointing up. So each axial substituent has 1,3 diaxial interactions. So we can just make that note, lots of 1,3 Diaxial interactions, remember 1, 3 is relative. They're 3 carbons away. So this is the less or least stable. There are only 2. All right, so that's the chair stuff. That wraps up chapter 4. Yeah, that wraps up chapter 4. Thank you so much for your patience, and I'm very sorry that the power outage has impacted our campus this much. It's obviously out of my control, but I just want to sincerely apologize on behalf of, I don't know, PG&E and the university or something, that we're really doing our best. And as our last little thing, I just wanted to say bye. Thank you again for all your patience. This is my little Obi boy, and he's been helping with the video. Please feel free to reach out if you have any questions for us. Discussions should be running tomorrow, being Friday. And if we have any special, hey Boyd, if we have any special office hours, which I'll probably do maybe this afternoon or so, I'll definitely let you know about that. Yeah, once again, thank you. Have a wonderful day.